Okay. So take a look at this real quick. Okay, look, everybody look. There you know. Looks more like a teppanyaki. Okay, look. Okay, simple idea. If this doesn't click, well, you should, talk to me until it does. This shape, despite its complexity, if we use the same idea we did with area, where we have a complex area, but we say, now we're not going to find the area, we're going to find the area of rectangles that fit inside the area. We're going to take the same approach for something like this. Instead of saying, let's find the volume of what you see, we instead say, no, let's focus on something simple. Let's find the volume of that. And then just, find the volume of this. And then add them together. On and on and on. So I'm hoping you see the parallel. We've had problems like this, where you see a region, you're supposed to find the area of the region, but you don't. Instead, you find the area of rectangles that fit within the region. Are you with me? Okay. Same thing is true for volume. Instead of trying to find the volume that you see, you don't pay attention to that at all. You pay attention to what I call one slice of the volume. Test calls it a cross-section. So, like saying, if you look at the object like this and you cut it up, you create cross-sections, slices. And all you have to do is find the volume of the slice. You want me to talk more about the big idea? That's the big idea. Just find the volume of this. The volume of this is really simple. It is the area that you see in red multiplied by the tiny thickness. Maybe you may say it differently. Just wave at me. Cool, simple idea. So the next thing, you look at problem 1 on your purple packet. They give a region. That part's not new. You're used to that because that's like the ones we did on area. I went ahead and did this step where I find the intersection. You all know how to do that. I labeled one graph as F, one as G. You're used to that as well. The way they create they have two ways they create three-dimensional volumes for this class. One way is they do it by what's called rotation or revolution. So they take this region and they rotate it about an axis. So in this example, the axis is the x-axis. And when that happens, a two-dimensional region creates a three-dimensional shape. Here's a quick video that demonstrates the idea. So our old friend YouTube here. So there's a region. It's not exactly the same one as on your paper, but it's exactly the same idea. Here's a region. They're going to rotate that region about the x-axis. So I push play here. It's very exciting. So then there's the cross-section. Dumb thing to stop. There it goes. Questions.
That's how the wheel is.
So that's exactly the same idea. This was created with a different shape, but same idea. Wave if you need to see it again. Oh, yeah, why not? So much better the second time.
Oh, next time I need some popcorn.
Get out your 3D glasses. Here's another version of the same idea. Sit at my desk for this one. Hold on. So here's another version of the same idea. My mouse will work this far away from my desk. You guys don't just this part. I can't see whatever. Okay, look at your paper and notice. Okay, this is the same, this is the region right there. Right here? So that's the region on your paper?
Yep.
And then this software will cause that region to rotate. So there's the three-dimensional solid that's created.
So there's Perfect.
Okay, questions, anybody so far? So far, just big ideas, no equations or anything, just the big idea of you have a region, you rotate the region, you can create a solid. We're going to find the volume of the solid slice by slice. Questions?
Yeah.
Okay, back to the purple paper. The first thing to memorize, if the volume is created by rotation or revolution, then the back up a step, my bad. First thing to memorize is what I said earlier, that you don't try to find the volume of what you see. You try to slice up what you see and simply find the volume of a slice. Okay? That's all you do is try to find the volume of the slice. Focus on that. Just like before, we tried to find the area of a rectangle. The second thing to memorize, if it's created by rotation, then the slices are always circles. No exception. Sometimes, probably most often, the slices will have a hole in the middle, but you can also have volumes like so, where the slices do not have a hole in the middle. Questions? But it doesn't change the fact that the slice is still circular. Okay? Key thing. One, don't try to find the volume of this. Instead, find the volume of a slice. Second thing, it's caused by rotation. The slice will be a circle. So I'm hoping you can see from this image that if I were to rotate this object like so, the slice is going to look like this. Like that. That's half of the slice. The other half of the slice was going to be on the other side of the board. Questions? Can't see it. Go like this so I can do something more so you can see it. Cool. So all we've got to do is find the area of that. Sorry, water heater commercial. It's going to find the area of that. The thickness is easy, it's just very thin. So the volume of this slice is the area you see multiplied by the thickness. So here's how we do that. On your purple paper, draw the following. Listen to the words. The process is always the same. This idea is actually, in my opinion, if you discuss it in the right way, it's one of the easiest concepts on the entire AP test, even though many people feel like it is one of the most difficult. I was talking to Mr. Rector yesterday, and his wife is a math teacher at BYU, Idaho, and he mentioned that we're going to be talking about this, and she's like, oh, I hate that, they're so hard. And he's like, no, you're not looking at it right. If you look at it in the right way, it's not hard at all. All I have to do is remember, I'm finding the area of a slice, and the slice is a circle. The center of the circle is always the axis of rotation. The center of the circle is always the axis of rotation. So the center is right there. Everybody see that? So that means I draw on my paper a vertical line from the center of rotation, just wherever, just like I did with the areas. Go up until you hit the region. That's the radius of the center of the circle, like the part that got cut out. That's the radius of the whole, or the radius of the inner circle, the radius of the missing piece, the part here. Are you with me? Wait if you need me to show it again so you can see it. Okay, so just label that R subscript I. Look at that. Then the outer radius goes from the axis again. So you get to the outside of the region, just like you saw here. So that's going from the center to here. Questions? Cool. Just label that as the outer radius. R subscript O. Okay, super. Oh, please.
Wait, how did you know to go from that point of the x-axis?
So, oh, like this way?
Yeah.
Awesome. Take it for that. It doesn't really matter. So I could have also done this, Autumn. I could have said, well, that's like this exact slice. It would be located like such. I don't have a cutout for you, but if I were to come clear over here, then the thickness is going to be a really fat circle with a very, very small hole. You with me? But I do the same logic. I'd say, oh, okay, over there, my inner radius is this tiny little piece here. And my outer radius is this much larger piece here. So I'm picking the spot this way randomly. Is that okay?
Yeah.
Anybody else? Please, Eric.
Does it matter if it's rotated on the X or Y axis?
So if it rotates like this, the logic of the problem doesn't change at all, but a little bit of the math does. And so we won't talk about that today, but we'll hit that a little bit in the future. So there you go. Okay. All you have to do now is think back to what you did when you were finding area. When we had to find area, we had to find the length of vertical lines. And the length of a vertical line is always the y coordinate at the top, subtract the y at the bottom. So that's all I write down. I say my outside radius is going to be the y coordinate at the top, which is found using the F formula. Subtract the y coordinate at the bottom, which in this example is 0. Wait if you need me to talk through that. Okay. My inside radius, y coordinate at the top, is going to be the function g of x. Y coordinate at the bottom in this example is also 0. So now I have a formula for the inner and outer radius. Points for everyone. Why do both of these formulas contain the variable x? what's the purpose of the x within the formula for the outer radius and the formula for the inner radius? Hands up. Why does each formula have an x? For Jonathan?
It's the position on your x-axis. It's how far across it is.
Perfect. This solid object, which is a little easier to see here, that solid, again, we're not thinking of it as a solid. We're thinking of it as a whole bunch of slices. And every slice is located at a different spot on the x-axis. So our formulas have to have an x to indicate which slice. Back to Autumn's question, really, what was I doing here? Why didn't I come here? Well, it doesn't really matter. The x takes care of that. So who had their hand raised? Show me. 2 points, 3 for Jonathan. Question. Please.
Why is f less than 0?
So, again, keep talking if this doesn't help.
Okay.
When we were finding the area of spaces, we talked about how anytime you have a vertical line on a graph, you can find the length of that vertical line simply by taking whatever the top y coordinate is and subtracting the bottom y coordinate. So that length would be 9. So I did the same thing here.
So like, where? Isn't the bottom of the region g of x not 0?
So the difference is, how do I say this? I'm not paying attention to the bottom of the region. I have to imagine that I can see the slice. Like I can't see the slice, I have to imagine I can see it. So if the slice is here, like that, you good with me? I've got to find the area. Somebody stole the circle from me. There was a circle that fits in that hole. I've got to find all of this area first. Once I find all of this area, I'm going to subtract out the area of the hole. So the outside radius is not, I'm not paying attention to this dimension here. And hold on. I'm not paying attention to this dimension at all. That's not important when I'm finding this particular volume. What I've got to pay attention to is the radius of the entire slice, which goes from here to here. Where on the drawing, that goes from the axis of rotation all the way to here. So I've got to pay attention to this dimension because that's the radius. It's the radius of the slice itself. I don't know if that helped.
Yeah, no, that did.
Andrea?
Why would you just not go from f of x to g of x? Like, why on like one finding out?
So are you okay that if I pull out the slice and look at it, f of x to g of x is from here to here? You see that? There's no mathematical way to use that to find this area. The only way to find this area is to find the area of everything as though there's nothing missing, and then subtract out the missing piece. Does that answer your question? 2 more. Anybody else? Oh, please.
So you said you did the top line, which is the whole radius, which is like the radius out and the radius inside, right?
I see what you're saying, but you don't want to quite think of it quite that way.
Okay.
But
Well,
you- go
I'm
ahead.
just confused, like why you have 2 different expressions for it, like the RO and RI.
No worries, just keep talking until this really feels good. No, I'm serious. Like, everybody, look, it really is the key to the entire year, but today is always, just keep talking until it feels good. Are you okay that I'm really just trying to find the area of what you see here? Okay, just the brown. But to find the area of the brown, it's going to drive me crazy that I can't find the circle. Somebody took the circle. Ah. Oh, I know why. I took the circle. I cut it in half. It fits in here like so. There we go. Jesse, blue, red line. Okay. You with me? Okay, so I'm trying to find the area of that circle. So the area of that circle is simply take the radius in the center and go all the way to the outside. You with me? Okay, on this drawing, that distance is from the axis of rotation, which is the x-axis, all the way to the outside. So for the outer radius has nothing to do with g. The outer radius has absolutely nothing to do with g. Okay, hold on to today. Does that make sense? The radius of the cutout, that's g. So the radius of the cutout has nothing to do with that. So it's, you can't think of them together. You have to think of them separate. I don't know if that helps. Okay, anybody else? All right, next step. So raise your hand again. I'll pay the whole room. Just want to make sure we're all together. What is this formula calculating? Hands up. What is that formula calculating? That I underlined in brown. Daniel.
The radius from the center to the most outside line.
Nice. It's calculating the radius of the entire circular slice. The entire circular slice as though there is nothing missing. The entire circular slice. This one's easier to hold. Like that. It's calculating the area of the entire, it's calculating the radius of the entire circular slice. How many knew that? 2 points, 3 for Daniel. All we have to do now is take that radius, square that radius. So take f of x. Move this out of the way here. Oh, I want it to disappear. Down here will work. So take that radius, f of x, subtract 0, square that radius, multiply that radius by pi. Hands up, please. What's that calculating? Come on. What's that calculating? And on the front.
It's f of x, it's making the area of the whole outer radius.
So that calculates the area of the entire circular slice. How many knew it? 2 points. 3 for Daniel. Hands up again. What's the purpose of the x in the formula? Come on. What's the purpose of the x in the formula? Paul.
That is the location.
Yep. Simply the location of the slice. How many knew it? 2 points. Now all we do is we must subtract away the cutout. So that's going to be pi g of x, subtract 0, squared. Question. This now becomes the area of one slice at whatever x you specify. A lot of parentheses on this problem, don't mess them up. All of that gets multiplied by dx. Now we are calculating the volume of one slice at whatever x you specify. The only purpose for integrating is to do it many, many times. I called the intersection B because I don't like using A. That's the answer to the problem. Plug it in your calculator, you're done. Question. Please.
Are we supposed to plug it into our calculator?
Yeah, this one's a calculator problem. So, but easy because just like we practiced with area, you put the f of x in y1, you put the g of x in y2, it goes really fast. So, points for there, please, Allison.
Okay, I'm still a little bit confused about the, so, the way you did this for the outside radius, you did f of x minus, like, what the outside radius and the inside radius.
So let's, you're doing great.
Like, I understand that, like, you need to find it all, but, like, and not like the inside.
Gotcha. Let's just keep talking. You're fine. This alone, entire room, hands up. F all by itself, what does that calculate? Hands up, come on. Like, what does f of x alone in any problem calculate? Like, forget circles, just f alone. You have an f of x formula, what does it always calculate? Every single problem you've ever worked in your entire life. Nelson?
Sorry, what's the question?
No worries. What is f of x, like any problem you have ever worked, ever? A formula called f of x, you plug in an x, you calculate something. What do you calculate?
The game of y.
You calculate the y coordinate. How many knew it? 2 points. So right here, when you see f, you should see a y coordinate, like this. Okay with that? So if I take that y coordinate and I subtract 0, I'm taking a y. I hate this board when I stand on that side. It just doesn't work on that side. Come on. It's like angry at me now. Okay. So I'm taking this y coordinate and I'm subtracting this y coordinate. So that gives me that length. Good? Okay, now I have to imagine it. I cannot see it on the board. I have to imagine the slice, like so, and I recognize that that length I just drew is exactly the same thing as the radius of an entire circular slice. You see it? You see it?
Yeah.
So from, it's hard to hold this, but from here to here, exactly the same thing as from here to here.
Yeah.
So that's why this, hands up again, whole room, come on. What's the blue box calculating? Hands up, come on. In this problem, what is the blue box calculating? Matt in the back.
The outer area.
Say it louder, Matt.
The whole area of the circular slice.
Well, the blue alone is only calculating the radius of the circular slice because it's only the dimension from, yeah, it's hard to hold this, here to here. So that's what the blue is finding. Hands up if you knew that. Come on, be honest. Keep them up, keep them up. 2 points. That's the blue. But if I take that blue and square it, multiplied by pi, I now have all of the area that you see me holding. Good. I must now eliminate from that this area. So what you're really doing is you're finding the area of 2 circles to find the area of the donut kind of a thing. So, hope that helps. Anybody else? That's it. Okay, if the big it says always in this class, if the big ideas make sense, they can throw any problem they want at you and you won't have any trouble with it. But don't try to focus on the steps, focus on the big idea. Okay, next thing. So that's one way they will ask you to find a volume that is created by rotating. Okay? But you don't care about the rotation other than to remember, oh yeah, when a volume is created by rotation, every slice is a circle. That's all you got to remember. Because all you care about is the slice. You don't care about the shape. Like, it's interesting to me to show this here, because I do think it helps your brain feel comfortable with the idea, but I really don't care what this thing looks like. If my only task is to find the volume, I don't care what it looks like, because I just know that every slice is a circle. And I don't spend any mental energy on the AP test trying to visualize that thing, because it won't help me answer the question. Okay, next thing. The other way they will ask you to find volume is instead, so go to number 2. So instead of saying, okay, the volume is created by rotating, what they do instead is they say the region now is flat. So there's a 3-dimensional solid you have to imagine being on the board, but now instead of that 3-dimensional solid being round, like you saw here, you now imagine the three-dimensional solid has a base that is flat, and the region is the base. This is out of control here. The region is the base. So go back to here. So what you see here is the flat part of the three-dimensional solid. And then the solid is created by stacking on top of that region slices of a known shape. In this case, they tell you that the slices are squares, like so. There they go. Oh, here we go. Just gotta keep looking. So the slices are squares like this. Like that. So we're going to find this volume now. There's nothing round about it at all. Okay? And the way these work is this whole thing fits on the region something like that. The idea being that every slice, just like the circles, has a different shape. The slice that fits over here is very small because it has to be squared and it has to fit on the region. So there's only this much space in the region, therefore the square can only have this much length. It has to fit there. This square cannot fit over here. This is the worst video ever if you're not here live. There? Yeah, good luck for those at home, sorry. Doing the best we can, but there's just no way to show this without, you know. Got it? If I take the medium-sized square, it only can fit, it can't fit there, it's too big. Can't fit here, too small, just like 3 bears, fits there. Just right, Daniel.
So, why are we solving it this way where we could just solve it in the way we've done previously where we find the area of that whole thing with cross-section is just lines and then multiply it, the whole thing by the thickness, however thick the solid is?
Oh, it's because the thickness of the solid changes every time you move.
Oh, I thought we were just saying like a solid and it was the same thing as a liquid. I see.
Do you see it?
Yeah, I was just imagining
It
like a bunch of papers that shape stacked on top of each other. So
Oh, no, not stacked this way. They're stacked on edge.
I see.
You see it? Here's some software that helps. This one. I have to go to my desk to control it. It doesn't work very well on the board. Look at the board. Do you see the region? Anyone need help seeing the region? So now, so here's the region. Look, right here. Here's the region. You're going to stack on top of that region slices. Every slice is the shape of a square. Here we go. Look at it. Come on, don't talk. Focus. Look. Now I've stacked onto the region. Each line you see is a square. You can't see that they're squares because you're looking at the edge. So if I grab the rotation button, watch what happens. Oh, hold on. Gotta fix it. Yeah, I had the wrong setting. Try again. There we go. So as I was saying to Daniel, the square is a different size depending on where it's located. Watch the orange. Please.
That's not revolving around anything.
No rotation at all. None. Yeah, no, 2 points for Carl. Listen to what he just said. It's crucial. This problem, when it's formed by rotation, the slices are circles. Otherwise, the slices have nothing to do with circles. There's no rotation. There's nothing round about it at all. You fill the space with many, many so like Daniel in the front was saying, yeah, we're gonna find the volume of that square piece. And then another square piece, another square piece. The trouble is every square piece is a slightly different size. And there are millions of them.
Hexagonal.
Like so. Now here you get a sense of what the 3D object actually looks like. See how it's flat on the bottom? That's the region right there.
Oh, really?
Dragons in the same place.
Side of the graph. See this right corner? Taking cross section. Cross sections.
Okay, questions from anyone?
Yeah, I think it was a shit too.
Okay, look. Again, don't spend any mental energy trying to visualize the shape. It doesn't help you solve the problem. All you have to do is say, okay, got my region. I know that right here, that's the edge of a square. I just can't see the square because it's on edge. But I just need to find the area of that square. So now, back to Allison's question, now F and G do work together. Before they didn't work together really, they were separate. Because F was being used to find the area of the entire circle, G was simply being used to find the area of the cutout, and that's always true on the rotational problem. Now, F and G absolutely work together because the length of the green line is nothing more than F subtract G. This is probably a silly question. I'm going to ask it anyway. Raise your hand and tell me now, what does that calculate? Hands up. What does that alone calculate? Come on, Edward.
It calculates the length of the distance between the two lines.
Perfect.
At any given point.
Perfect, perfect. That's the purpose of the X, is to specify where. You know, if we want the big square, it's over here. We want the tiny square, it's over here. It's the length of one side of a square slice. How many knew it? 2 points. I need the area of the square slice. I need the green. It's square. It can't be easier. Please.
Will they ever have you like say they want this shape, but instead of like just a square, like some weird short like rectangle, like to raise it up higher or shorten it down or something? Or
So the most common thing they do is, let me finish this. Stay with me. Hey. So this is now the area right here. This is the area of one slice at whatever x you specify. Multiplying by dx, I get the volume of one slice at whatever x I specify. Now I just need to do that computation over and over again. Done. Pick up my calculator, collect my points. Question. I sincerely hope that on the AP test you encounter a problem in FRQ, these are common in FRQs, where they have this kind of a question because it's worth 9 points total. Okay? 9 points total is about 1/6 of all that you need to get a four on the test.
Are you serious?
That's good news.
So easy.
What's that?
Can we just get 6 of those?
Yeah, unfortunately they won't do that.
I like if you blew it up, then you're in big trouble.
Well, there's always the pessimistic view, you know.
I think that's why he was.
Oh, that's why he's.
That's why he
It
was.
was unrelated.
Oh, my God, my apologies. Sheets of planet. Please.
Will there ever be like a problem with like find a square or find a triangle or find a shape?
Close. That's what Carl was saying. Hey, look up. Okay, so what you have to be prepared to encounter is problems where the solid is created by rotation, and then the slices are always circles. Problems where the cross sections are some known shape. Square is most common. I'd say second most common is semicircle. So the slices have the shape of a semicircle. The idea doesn't change. You just stack semicircles onto the region. Like here, for the viewing folks at home, if I change the shape from a square to a semicircle, come on, go away. There you go. Now they are semicircles. It's hard to control from the board. Like that? Can you see it? Carl, please.
So then you just like, to get that, you get f of x minus g of x, like half, 1/2 to that or whatever. And that would give you the radius of that. And then you go like half of pi r squared to get the volume.
Super
Right.
close. No, you got the right. Your thinking is right. Your math's just off by a tiny bit. But I don't care about that. Look at me. The compliment I just gave Carl is key to the class. If your logic is in the right place, like you're thinking of the big idea correctly, it doesn't matter that your math is off a little bit, because it's really easy to fix. What's impossible to fix is when you can't explain the big idea to me, and all you can do is say, well, I'm pretty sure the step is this. And I'm like, why? And you're like, I don't know. Then you're in trouble. Okay? So Carlos correct. The big idea is really simple. If the slice is a semicircle, what you are looking at when you look at the board is the edge of the slice, which is actually the diameter of the slice. So like this, if that makes sense. Come on. You're seeing the diameter of the slice, 2 points. For all who did this. You're seeing the diameter of the slice. So I prefer to use a much simpler formula. I just memorize it. You can use other formulas, but I like this one. The area of a semicircular slice is just diameter squared times pi over 8. Okay? You learned it like this. You said, oh, the area of a circle is pi r squared. Therefore, the area of a semicircle would be 1/2 pi r squared. That's true. And you can use this. There's nothing wrong with it. It's just that I don't see the radius very easily here. I see the diameter. So I just memorize this. Pi over 8 diameter squared. Logan.
Is it always pi over 8 or is that just
Always pi over 8 for a semicircle. Yep.
Is that because it's like 1/2 like for the semicircle and then a fourth because it's like the diameter?
Here's exactly what happens. If I take the diameter and I need to make it the radius, I have to half that, right? And then I square that radius, multiplied by pi over 2. That's the area of a semicircle. But because the 2 is inside the squaring, what you really have is pi over 2 diameter squared over 4, which means you really have pi over 8 diameter squared. So that's the area of a semicircle. Anybody else? Awesome. Back to Carl's question. So semicircles, squares. There's one in the homework where they say it's a rectangle. I did my best to draw it. It's not a very good drawing, but hope you can get the general idea. So here's the region down here. I've tried to kind of give a three-dimensional kind of view, although I'm not very good at it. Now the slices that sit on the region are rectangular. You with me? It's not hard though. The edge of the rectangle is right here. The edge of the rectangle is still f subtract g. The edge of the rectangle is still F subtract G. With me? But now I've got to multiply by this dimension here, which in this case is 5 times this dimension. F times F minus G again. Okay, raise your hands please and tell me. What is this calculating? Hands up. What's that calculating? Come on. Looking for a few more. Let's go miles.
The area of the rectangle.
Perfect. It's the area of one slice. X represents which slice? How many knew it? 2 points. Okay. All I have to do now is multiply it to. Those are factors, so I actually don't need another set of parentheses. Just put a dx on there. Perform the operation in this case from B to 1. That'll find the volume of the solid.
For that, then just to like make sure, could you do like fx minus ax squared?
Oh, for sure. Either way. Yep, either way. Please, Alice.
Why do you do f of x minus g
That's what calculus is.
So, are you okay that the length of this line is F minus G?
Yes.
Awesome. Are you okay that in this problem, I have to imagine that that length is one side of a rectangle? I can't see the rectangle because it's on edge. With me? Something like that. Good? So now I have to multiply by the long dimension of the rectangle. So right here, this is F minus G right there. But now I have to multiply by the long dimension of the rectangle, which is 5 times F minus G, because they told me it was 5 times more. Does that answer your question? There we go. 2 points. There we go. Sweet. Back to Carl's question. There was a question on the AP test that, in my opinion, if you understood the big idea as you read the question, you would be celebrating. You'd be going, awesome, they are giving me a question that half the world's going to miss, so that'll help the curve. I'm going to get it right because I understand the big idea, okay? The question said something like this. You have a region. The cross sections, every cross section is a function of x, meaning the area of the cross section is different at different x values. And then they simply gave a formula for computing the area of any cross section. Something like this, I don't know. Okay? So all you had to do was say, oh, they did all the work for me. I don't know what the shape of the cross section is. They didn't tell me. But they told me what I have to know. I have to know the area of the cross section. It's right there. So all I have to do is take this area, multiply it by dx. Now I have the volume of a given cross section. I just need to compute that for many, many x's. And that's how you solve that problem. Because the whole idea is it's always about the cross section, not about the solid. I hope that answered your question. Okay. Other questions? Please, come on. No.
I don't know if I'm moving forward, but I was looking at number 5, and since it's rotating around a more vertical axis, does that mean you have that you're only implying a horizontal cross section?
3 points for math. You misread it slightly, but it's still a good question. If it is rotating like so, my hand, then there is some math we've got to do to adjust for this. It doesn't change the big idea at all. So like I said to Carl earlier, focus on the big idea, you're in good shape. What did change here is instead of rotating about the x-axis, it's rotating about a line that's up here. Yeah, no worries. You good now so far? Let's keep going because it's a good question still. you'll see one in the homework where the axis of rotation is down here. Okay, the big idea does not change. Don't change the way you think about the problem. Just think like this. Okay, wait a minute. My axis of rotation is up here. Like so. That's my axis of rotation. That means the slices, let's see, the radius of a slice is going to be right here. This is going to be the radius of the big round slice. Like that. That's the radius of the big round slice. Because this is the center of the slice. It's going to look something like this. So my shape doesn't quite match up, but it's something like that. Questions? So same logic. I've got to find the length of the purple line. I just take the y coordinate at the top, which is 1. I subtract the y coordinate at the bottom, which in this case is g. That will calculate the radius of any slice. Question? Please, come on. Shoot, no, we're done. Oh, go ahead. Jonathan, David, sorry.
So in the end, are you kind of calculating like a donut kind of thing? Like if we just do this?
This one, it's not really a donut because it has no real hole in the middle, but kind of a
Something
thing.
to that effect.
It's kind of like a donut that ain't really, it's
It's
kind of
kinda
a
like
pastry, you know. Yeah, again, you know, you can kind of sit and try and think what it looks like. It's not really that important, but it, you know, I don't know, it's kind of interesting. Like, here we go. So the region there is pretty similar, fair? All I have to do is change the rotational axis. Let me do that real quick. Answer David's question. Okay, so notice.
So this is being used for like 3D rendering, right?
Here's the region. Look, come on. Here's the region. Now I'm going to rotate it about a line that's up here above. There we go.
Make a donut.
It is a donut.
Those are like points.
It's a donut, but it's not like a perfect circle through the neighborhood.
Yeah, watch this. Hey, last thing before the bell, look. If I move that line higher, to say 2, now you're going to get a pretty good sized hole in the middle.
It is like a donut.
That's like an upside down.
Keep watching. They'll also have you do a rotation where the line is below. Watch this. Like -2. -22. Never mind.
Wow, that is a big ball.
So it rotates that way. Your logic doesn't change. Question. Good job. See ya.
We come back and there's like just 3.
Johnny Cash?